Hello everybody, Mr. Hasty here. Today we're going to continue our discussion of fluid dynamics with the discussion of fluid force. So we understand the concept of force. Force is how much oomph, push, pull that something has. And we're going to talk about it in relationship to pressure. So what is pressure? Pressure is force distributed over an area. Now, literally, there are two ways to calculate fluid force. Pressure. One of them being that it is force divided by an area. So the concept of pressure is as follows. If you have a certain amount of force, let's just say 10 pounds, and you focus that force into a very small area, it's going to generate a lot of pressure. But if you generate over a rather large area, it creates less pressure. Right? That's why you'll allow someone to poke you with their finger, but poking you with the point of a knife, much smaller area would hurt. Now, for water, or for liquids in general, this has a very interesting property, and that it's purely tied to the height of the liquid in the container. So if you've ever messed around with liquid in a container, and I think you do something with this maybe in Algebra 2, and you poke a hole in the bottom, that stream will shoot out. But as the water gets lower, the stream gets shorter with less force, with less pressure. So there's another formula that is equivalent to weight density times height. So you can look at it just as the weight density of the liquid times the height of the liquid. Now, when we work through this, we're actually been looking for fluid force. And so I want us to focus on this part of the equation. With some algebra, we can say the fluid force is equal to weight density times height times area. The area of what will be dependent on what shape we're applying this to and how we're applying it. So just a reminder, weight density is how many pounds per cubic foot a liquid has. So if we analyze our equation for force, we have pounds per cubic foot. The height of our liquid could be measured in feet, and the area would be measured in feet squared. And we get all the cancellations. This would combine to be cubic feet, canceling with the bottom to get pounds, which is a measurement of force. So instead of just diving into the example, we're actually going to use an example of engineering failure from history. So, the Great Molasses Flood of 1919, this is a real thing that happened. And I've actually learned about this from the textbook. I'm going to read an excerpt from the textbook. At 1 p.m. on January 15th, 1919, and on an unseasonably warm day, a 90-foot high, 90-foot diameter cylindrical metal tank in which the Puritan Distilling Company stored molasses at the corner of Foster and Commercial Streets in Boston's North End exploded. So real quick, let's get a concept of this. We're talking 90 feet wide, that's 30 yards, right? Which yards for some of us are easier to think about than feet. And 90 feet tall, that's 30 yards high. That is a relatively massive container or something. And it's filled with molasses. Molasses is a pretty thick substance. So molasses flooded the streets 30 feet deep. Think about that. 30 feet deep. That means 3 basketball rims in height deep. Trapping pedestrians and horses, because they still used horses for locomotion at this time, knocking down buildings and oozing into homes. It was eventually tracked all over town and even made its way into the suburbs via trolley cars and people's shoes. It took weeks to clean up. So that's all from the textbook. But that's just a massive disaster for the size of thing we're talking about here. It's basically just that our container was not built to withstand the amount of force being exerted on it. Now, as I will talk about, a lot of containers that are dealing with something this large are actually designed so they flare at the bottom. So basically, the bottom is thicker to help withstand force. That's actually how we built dams. Like the Hoover Dam is built like that. But a cylindrical container wouldn't be thickened out at the bottom necessarily. So we're actually going to figure out how much force was being exerted on the bottom of this tank. Now, it's more interesting to talk about the bottom because there's more force. As the liquid gets higher, there's more force towards the bottom. So, given a 90-foot high, 90-foot diameter, so we're just going to label our stuff here, 90 feet diameter, 90-foot high. This is all from the actual dimensions of the object. Filled with molasses. Molasses has a weight density of about 100 pounds per cubic foot. So let's think about that a second. We can all imagine a box that is 1 foot by 1 foot by 1 foot. And we're saying that one of those boxes weighs 100 pounds. So, if that's true, well, that's terrible pounds. If that's true, this is a pretty dense liquid. It's pretty heavy. So, we're going to ask two questions. The first is, what is the total force exerted on the bottom of the tank? So, this circle on the bottom. And what would be the force exerted on the bottom 1 foot band along the wall? So that'll actually be along the side, and that's going to involve calculus. The first part, not going to involve calculus. So, the formula we derived a little bit ago is that the force is going to be equal to the weight density times the height of the liquid times the area it's exerted on. We know the weight density to be 100 pounds. We know the height of the liquid. For if this is filled with molasses, this tank is filled with molasses, the liquid was 90 feet high. Now, for every point, this is important, this is why we don't need calculus, for every point on the bottom, the liquid above that point is 90 feet high. And the area, well, we're just talking about the area of the circle on the bottom. So area of a circle is pi. The radius would be half the diameter. So we're talking 45 squared. And that's it. That's all we got to do. We do the math there, and we are going to get 57,255,526.11 pounds of force. Quite significant. So, what about the bottom 1 foot band? Well, this gets a little bit tricky because if I'm gonna blow that up, I'm gonna draw a bigger picture. Let's imagine that this is only 1 foot thick total, though. So, the height of the liquid exposed to this part of the band is different than the height of the liquid exposed to that part of the band. In fact, at the bottom it'd be 90, but at the top it'd be 89. And so what we're going to have to do is we're going to have to cut this into little rings. And how thick? Well, remember, in calculus, the smaller the ring, as it gets infinitely small, we get infinitely accurate. So the thickness of those rings is going to be delta y. We're using y because we're going up and down. So let's go through our process again. Force is equal to weight density. Weight density has not changed, 100. The height, this is where it's interesting. The height varies. The height varies depending on how far down it goes, and there's two ways to set this up. So we could say 90 minus y, if we're talking about y being from the bottom, right? Or we could just call it y, which is simpler. So we're going to call it y. And again, you could call it 90 minus y. We'll talk about that here in a second. And then the area is what's going to get interesting here. Because we're not talking about a circular area. We're talking about an area of a band, which is around the outside. So imagine that I took that band out and I cut it. It's going to form a rectangle. And we've done this before. That rectangle is delta y thick, but the length of that is the circumference of the circle. So it would be 2 pi r. And we know r to be 45. So the area of that band, of each individual section of that band, is 2 times pi times 45 times delta y. Length times width of that band. Because remember, if you visualize it, if you go around a rectangle and you were to take that band off, that thin ribbon, and cut it, you could turn it into a rectangle. And the distance around the circle, the circumference, would be the length of that rectangle. Because it has a delta y, we're going to use calculus. So our force becomes an integral of 100y times 90 pi, just simplified there, dy. Now let's talk bounds. If y represents the distance from the bottom, then what's the height at any given point? The height here would be 90 and the height here would be 89 because this is a 1 foot band total. So that means the lowest the height could ever be is 89 and the highest it could ever be is 90. Now the alternate setup to this would be an integral from 0 to 1 of 100 times 90 minus y times 90 pi dy. So let's explain that. This and this are going to come out the same numerically because this value is going to go from 89 to 90, and this whole parentheses is going to go from 89 to 90. So it's the same thing no matter what. And when you do either of these integrals, you get 2,530,552.9 pounds. So all this force being exerted on the bottom of the tank ended up making the tank explode, hence causing the engineering failure. So on these problems, we are typically going to be working with cylindrical tanks. If it was not cylindrical, we would just need to adjust our area formulas. I think one of the problems in the book would be, and we're going to go to a general approach section here. One of the problems in the book is going to be a rectangular prism, so something that would look like this. And in that case, we have to realize the bottom would be a rectangle, but the bottom thin band, the calculations here are going to be very, very similar. We're just going to have a band, if we pop that out, if we were to cut it out and stretch it out, equal to the perimeter, however we have to model the perimeter, and a thickness of delta y, and do the integral of those. So no matter what shape, we can do that methodology. And in every situation for this, when we are trying to calculate the force exerted by a fluid, we're going to do weight density times height. Now the height is oftentimes going to be a variable because the height would change if we are talking about the top of the region or the bottom. And we have to multiply by the area of the region, and that's where we're going to use something like this. That is almost always going to be where we get our delta y or delta x, and then because there's a delta y or delta x, that means we're going to need to integrate. Alright guys, that's it for today. Hope things are going well. See you next time.